So in this sequence, we're going to talk about an introduction to deep learning. And this introduction is not going to be technical. It's more like an overview of looking at how deep learning fits into the context of other areas and maybe what makes deep learning very popular now. So why is deep learning so popular now? One reason is that it just works a lot better than traditional machine learning algorithms as the data size increases. So probably in the beginning, like 2010, 2011, people started to notice that on traditional problems, deep learning approaches were achieving fantastic results, and they got really excited about it. And then that led to a lot of investment in deep learning, and then the results got better and better. Of course, there's always a question of like what was really achieved and when does it work. And so there's a lot of nuanced discussion there. But I would say overall, there are a lot of topics where deep learning has created huge improvements. So there are significant improvements on problems where large data sets are available or have been collected. And that is also one obstacle to deep learning, that the data sets generally need to be large. So here's a graph that is copied from Andrew Ng. And what you see in this graph is more like an abstract idea that on the one axis, so you see here on the x-axis, there's amount of data. And we just think about some machine learning problem, and we want to know how does the performance of a machine learning algorithm improve or not improve as the amount of data increases. So on the y-axis, we have the performance. And if we look at the traditional machine learning algorithm, then what we have this curve is that the more data, the better, but at some point it will saturate, and then additional data will not really bring additional improvements. And then if you use a small neural network, it will go up, and it will go up more, and then it will eventually also saturate, but it will saturate later. And overall, if you have enough data, so let's say that you're at the point here, the small neural network will outperform the traditional machine learning algorithm. And then for a medium neural network, it will be even better. So it will saturate later. And if you have enough data, the medium neural network will outperform the small one and the traditional machine learning algorithm. And then if you have a lot of data, then even this large neural network will pay off, and you can make use of additional amount of data. And so when you look at some of the large neural networks, maybe in the context of natural language processing, these networks are really, truly very large. So even with a small cluster, you have no hope of ever training these models. That's kind of how big they have gotten. Why is deep learning so effective now? One thing that changed is the availability of data, and also probably the availability of data to the research community. What happened is that just some larger data sets were collected, and in particular, one very important data set is ImageNet, that is a collection of 1 million plus images that are labeled, that just help a lot when you want to start out on doing research on deep learning. Because if you think about starting a project by yourself and you have the daunting task of collecting the data yourself, this is actually very, very difficult. So how can you get 1 million images and label them? This is not a small task, especially for a master PhD student. This is not something you can do on the side. But nowadays, for a lot of problems, there are standard data sets that can be used, and you can just use the standard data set and start working on the problem. For example, image classification, object detection, segmentation, depth estimation, detecting humans, all these type of problems have standard data sets that are available and can be downloaded. Now, at the same time, there's no reason to get overexcited about the availability of data. What many people find is that when they want to work on a problem, that they always wish to have more data. They wish they had higher quality data. Maybe they have only images in lower resolution, they want them in higher resolution. The images might have JPEG artifacts or they have lighting artifacts. They're not taken in a way that maybe they avoid certain other defects like occlusion. And so it's still a big struggle, but probably compared to 10 years ago, availability of data has become a lot better. Next, hardware. There has been a lot of improvement in hardware that enables good performance for deep learning and for training neural networks. So very popular nowadays is NVIDIA's hardware that also improved a lot in the last 10 years. And a lot of people, they use NVIDIA cards that were traditionally built for computer graphics for deep learning. And these cards are available in consumer versions and they're available in data center versions. And the hardware, these dedicated GPUs, they provide a huge speed up over regular CPUs. And also there's some other architectures, and I guess a lot of other companies are trying to build more dedicated hardware for deep learning. So one example is Tesla. They built their own deep learning hardware for their cars. Another example is Google. They have their own TPU architecture that they are using for their deep learning. And I think this is a very active area where we will see possibly a lot of changes in the next even 1 to 3 years. Next, there's a great community. So if you want to know about deep learning, you will find tons of material available freely on the internet. There will be blog posts, how to get started, or discussing latest research. There will be a lot of GitHub repositories where people post the code for their papers, so you can just download some of the latest models and just run them. And if you do research, you can start with something that already works really well. You just download an existing model and try to modify it. This brings a lot of acceleration. If you want to start out, it's very difficult to build machine learning models from scratch, but downloading something that works from GitHub and starting from an already well-working starting point is a lot easier. There's archive. People in the past, they submitted papers to conferences, and then it takes maybe half a year for the paper to get published, and then only afterwards people read your paper. Then after the conference, they think about what can we improve. And so let's take, for example, CVPR. They might have a deadline, let's say in the middle of November, but the paper is then published in June. But nowadays, people submit in the middle of November and put the paper on archive in the middle of November. So you see the follow-up work to papers that were published in November. You see it 1 month later, 2 months later, 3 months later. and not 8 months later as it was in the past. Now, tools, if you want to start using deep learning, you're basically using some extension to Python, such as TensorFlow, PyTorch, Keras. These are deep learning tools that you use together with Python, and that have a lot of functionality that makes it easy to build and train neural networks. So if you think about implementing a neural network from scratch, really in the sense that you have to write the optimization, all the training routines, this is just a huge undertaking. And with these tools, you can build neural networks more like a construction kit. You said, hey, I want to use this optimization. I want to use this loss function. I want so many layers of this type, and go train it for me and go run it for me. So the code, instead of many 10,000 lines of code, you can create the working neural network in, I don't know what, let's say 20, 30 lines of code. Investment, we've seen a massive amount of investment from big companies in deep learning. For example, Google, Facebook, Microsoft, Amazon, Alibaba, Tencent. So huge companies all around the world invested very large sums of money in these projects. And you can also look at some trends within the companies, like how many of the projects these companies have involve deep learning. You will see that this is a sharply increasing curve, where you have probably maybe the majority of projects at the company like Google might use deep learning now. So where is deep learning in the AI hierarchy? Deep learning is considered to be part of machine learning, and machine learning is considered to be part of artificial intelligence. So you see that AI is kind of the umbrella term. Within AI, we have machine learning, and within machine learning, we have deep learning. However, this is not drawn proportional to its size. The AI circle is almost completely filled with machine learning, and the machine learning circle nowadays is almost completely filled with deep learning. So that deep learning might be 90% of machine learning, and machine learning is 90% of artificial intelligence, if you think about it as maybe size of the research community that deals with these topics, and maybe also if it's about industrial interest in these techniques, this might be similar proportions. Now, I'm not totally sure about that. That's just my intuition or perception. What are major topics of in artificial intelligence itself? Now, of course, machine learning, which is related to this course, is a big topic in AI, is the biggest topic in AI. And but then besides machine learning, let's just look at some of these topics. I would call them traditional AI, such as search. You hopefully have heard of A-star search, planning algorithms, knowledge representation, game theory, probabilistic graphical models, logic. And if you're not very familiar with these terms, maybe you might want to look at this book, Artificial Intelligence, A Modern Approach. I think this is a very popular textbook that discusses artificial intelligence, traditional artificial intelligence. And you could maybe just start by going to Amazon and try to look at the table of contents of this book, just to look, if you haven't taken a class, what type of topics are discussed in artificial intelligence. Now, if you take an artificial intelligence class, you will also see that there's several subfields that are research fields of its own that might be classified as subfields of AI, such as data mining, computer vision, robotics, and natural language processing, and to some extent, sometimes computer graphics or maybe even bioinformatics. And this is probably, these fields are probably too large now to really call them subfields of AI. It's maybe a better view to think of these topics using a lot of methodology that comes from AI, and nowadays a lot of methodology from machine learning and more specifically deep learning. So if you go, for example, to a computer vision conference, a robotics conference, or a natural language processing conference, you might see the overwhelming number of papers are about deep learning. So how can we structure machine learning? One simple way that is often used is to distinguish supervised learning versus unsupervised learning versus reinforcement learning. Another thing you might have heard about is the idea to say regression versus classification. And one thing that is kind of very well known in the deep learning community is this LeCake, this analogy from LeCun, Jan LeCun, one of the founders, pioneers in the area of deep learning, that talks about reinforcement learning, supervised learning, and self-supervised learning, looking at it as parts of a cake. And specifically, what LeCun points out with this analogy is how much data is given to an algorithm to learn. So pure reinforcement learning is what he would call as the cherry on top of the cake. It's very, very small. And here the machine predicts a scalar reward that is given once in a while. So maybe you have a game of, you have a game, and then you are only given at the end, did you win or did you lose? So, or how many points did you score for playing the complete game? And this is very little information. So maybe here Jan says a few bits for some of the samples. Then underneath the cherry on top of the cake is supervised learning. And here this is the icing on top of the cake. So in supervised learning, the machine predicts a category or a few numbers for each input, kind of predicting human supplied data. So you would have 10 to 10,000 bits per sample. Let's think of image classification. You get one image, and as output you want to predict, is this a cat, is this a dog, is this a car, is this a tree? And so depending on how many categories you have, this will determine how many bits per sample you will predict. And overall, this is going to be a low number of bits per sample if it's image classification. If we think about depth prediction for an image or segmentation, then we will have one label per pixel. So this will be a lot more information per sample, but still not as huge of amount as the next category, self-supervised learning. And this LeCun compares to the main part of the cake. So in self-supervised learning, maybe the machine predicts any parts of its input for any observed part. Now, this is maybe not the best definition for self-supervised learning, but you could think of it as you're given a complete video and you try to predict future frames of the video given the previous frames. So why is this self-supervised? Because here the human doesn't provide any labeled data. So you really just try to predict one part of the data from other parts of the data. But here you have millions of bits per sample as information that is used. Now, for historic reasons, we'll give an image of the slide that Jan LeCun used. And here you can see his cake with the cherry on top and then the icing. And at the bottom, this is the main part of the cake. What are traditional machine learning tools? Again, neural networks, what we are going to study in this class. This is a big part of machine learning tools. But before neural networks, or besides neural networks, people studied and used tools such as mixture models and expectation maximization, such as k-means clustering. You have hopefully heard of KNN classifiers. So if you have a large set of data, you might just try to classify data by looking at what is in your training set, and if you want to classify a new set of data, what is this data similar to? So for example, if you want to classify an image, you could go to your image data set and just say what's the most similar image in the data set, and then whatever label the image in the data set has, that's the label I want to take. And if you do a voting of not just what's the closest, but what are the k closest, so we could go and say, let's pick the 5 closest images and then have them vote. So if the 5 closest images are 4 dogs and 1 cat, then the vote will be 4-1 in favor of dog, and then dog will be the assigned label to the new image. Now there's also decision trees where you try to create a tree to structure the space and assign decisions to the leaf nodes of the tree. So if there's a new data coming in, then maybe you traverse the tree, see in which node you end up with and what the decision is there. Another very popular, probably 90s, early 2000s, dominating machine learning in the practical sense were support vector machines, a great invention. There's logistic regression, another simple technique that you should have heard about, Gaussian process regression, graphical models. You hopefully have heard of Bayesian networks, kernel methods. The kernel trick is also a popular technique in machine learning. You have some simple tools, maybe derived from linear algebra, and some optimization, such as PCA, ICA. Then there's the world of sampling, Markov chain Monte Carlo, Markov models, boosting. Now, the idea of this course is that you hopefully have some, at least high-level idea about these machine learning techniques. So if you want to know a lot more about them, you probably have to take a class, or you pick up maybe this book, Pattern Recognition and Machine Learning by Bishop, and maybe start looking at the table of contents to get some idea what is this traditional machine learning about. And maybe you even want to just look at some of these topics and look at the Wikipedia articles, or look at some very quick tutorial to some of these topics to get some idea about what this traditional machine learning is about. Now, in this class, I will not review any of these topics, and it's not really clear how much of that you really need, but a basic understanding. If at any point in the course you feel you don't have a basic understanding of these techniques, the idea is you would just have to go and look them up. Now, let's say you want to do research in AI, then I think it really helps to know what are the major conferences in AI. And the idea is that if you want to start out, what I often recommend is that people go to the topic that they're interested in, pick the major conference, and look at 10, 20 papers that were published in the last edition of the conference. So for example, if you're interested in computer vision, then you would go to CVPR and you would try to look at 20 papers, but just looking at the abstracts and the images. And this should give you some idea what are people doing in the field of computer vision. So, but maybe if you want to do artificial intelligence, then artificial intelligence, the top two conferences would be AAAI and ICHCAI. If you want to do computer vision, it's ECCV, ICCV, and CVPR, where in some sense they are of equal importance, but in another sense, CVPR is just a bit more important than the other two. So what happens is that every year there's one CVPR conference, and ECCV and ICCV are alternating so that they're only being held every second year. Data mining, the top conference is SIGKDD. Computer graphics, there's SIGGRAPH and SIGGRAPH Asia. Traditional machine learning has ICML and NeurIPS, and deep learning has this newish now conference, ICLR, that is also very big now. So I think to give you some idea of the size of these conferences, if you look at ICLR, NeurIPS, CVPR, and maybe AAAI, I believe in the last year there were between 5,000 to 10,000 submissions for all these conferences. And this is a massive amount of submissions that has never been there before for any other computer science conference in the past. So the number of submissions has increased drastically. The size of these conferences, the number of accepted papers has increased drastically compared to what has been there before. Now, again, if you look at still where to start out, then I think one problem with traditional AI now is that it has machine learning, deep learning as part of it. So if you go to these conferences, you will see that they are a bit spread thin. So they talk about some of the traditional topics, but you will also see a large number of random machine learning papers. So actually, AI is probably not what I would recommend starting out with if you're interested in deep learning. I think the better way to start is to look at CVPR, which has a lot of the best practical papers in deep learning. And also you can look at ICLR and then maybe NeurIPS, but I would pick CVPR, ICLR, maybe NeurIPS as the top 3 conferences to learn more about deep learning. Now, one thing that's actually missing from this slide is natural language processing. So historically, I would say that computer vision was the driving factor behind deep learning, but in the last 1-2 years, we saw that natural language processing has kind of caught up and has created now, instead of only copying ideas that existed in other fields, that has created a lot of significant innovation by itself. All right, so what applications are examples of deep learning in industry? If you use Google and you type in a search query, then the Google search engine itself uses deep learning. If you are thinking, where does Google, Facebook, where do they get all the money from? That is dominantly by advertisement. And so the selection of ads for given users, for given content, is also done by deep learning. And then you have spam filters. That is a very important but now almost transparent technology that makes email usable, because otherwise we would all be drowning in spam. That uses deep learning. Voice recognition on mobile phones. So for example, I have an iPhone. There you can talk to Siri. That would use deep learning. Movie or product recommendations. So if you're using Netflix, then Netflix might provide recommendations. I guess they would use deep learning for that. But maybe with even higher economic impact, you would go to Amazon, and then when you type in some search, maybe you find the product that you want, but often it's not precisely specified. So they would use deep learning for finding out what are the products maybe that you're looking for, and what are other products we can recommend, probably with the goal of making the most sales possible. Credit card fraud detection. There are too many transactions to have humans looking at each transaction one at a time. So you would use deep learning to try to do some maybe initial triage of the data to maybe have some flagging, or even just automatically flag it, or maybe decide which things that the human should look at more carefully. Language translation. You can have fantastic language translation now from one language into another, and this would be done by deep learning. You want to translate English to Arabic, Arabic to English, English to German, German to French. There has been tremendous progress being made thanks to deep learning. Now, a huge topic that was very much hyped, maybe still is, maybe not, are self-driving cars, boats, planes, trucks. So the idea to replace like human-operated cars by self-driving cars very quickly, this might not look as successful as people originally thought it was, but still you see a lot of investment from car companies and many different companies to try to build self-driving cars, boats, planes, trucks. One example, also given by LeCun, who works at Facebook, is, let's say that in Facebook, users upload 2 billion photos per day. And as these photos are uploaded, they will go through multiple steps that are all conducted using deep learning. So within 2 seconds, each photo passes through 4 convolutional networks. First, image tagging. There are a few thousand tags. Is it a wedding, birthday party, landscape, indoor scene, dog, breed of dog, sailboat? So this would label the images. Then you want to do face recognition for automatic tagging of friends, captions for visually impaired, and detecting objectionable content, such as violence or pornography. So this is something from Andrew Ng, who is spending a lot of time basically publicizing artificial intelligence and machine learning and deep learning, and who gives a lot of high-level talks. So one thing that he mentioned, which I found was quite interesting, is internet companies, what did they do? And now basically trying to use that to explain AI companies, what do they do and what makes an AI company. So some decades ago, internet companies were a major trend, like the idea of AI companies now are a major trend. And so the kind of reminder that Andrew NG gives is that if you have a shopping mall and build a website, this is not an internet company. So the idea is that an internet company would be a company that organize the way it is run in such a way that it exploits what the internet lets you do really well. So it's not about having a website or not, but do you really use the benefits of the internet well? So some of these things would be A/B testing, short shipping times, not in the sense maybe that you ship a book in 2 days, but you can ship products and change products very quickly. So for example, you can have a website and you can change the software that runs the website really, really quickly. So you can launch a new product every day. And maybe if you have a shopping mall itself, like the physical building, this is maybe redesigned once a year or not even that. And then one idea is that you push decision-making down to engineers or product managers, recognizing that a lot of the decisions are too complex to be done by upper-level management. So they will probably still, need to make a fair amount of decisions, but probably you want to empower engineers and product managers more than this is done in traditional companies. Now, the analogy now for AI companies is that if you have a company plus some neural network, this doesn't make it an AI company. So AI companies are focused on strategic data acquisition. So this data acquisition is really important, and it can give you a really big advantage. So if you think about a company like Google, for example, they might not actually have to protect their deep learning algorithms that much, because the data is giving them a massive advantage. And even if you know the algorithm, you cannot simply build so many data centers and collect so much data to replicate the success. And if you have a deep learning company in some specific field, maybe you work in some medical field or you work in some agricultural field, and you work on something that has to do with image analysis, then you building a large data set of labeled images will be a significant competitive advantage. And so if you get more customers, then maybe you can collect more data from your customers, and at one point in time you might have so much more data than anybody who could hope to enter the market. Another example is Tesla. Tesla has all these cars on the road, and what these cars are doing is they are collecting data about traffic situations for the company. So this is a huge advantage. If you want to start with self-driving cars, where do you get all the data? I mean, these other companies, they might have thousands and thousands and thousands of miles and driving hours in all sorts of different situations. And if you want to start out, it would take you such a long time to catch up to this data acquisition deficit. Now, another idea is this unified data warehouses. I'm not really going to touch on that. And another idea is spotting pervasive automation opportunities is on a high level what in your company could really be automated, or what could be replaced by a deep neural network. And so one thing that Andrew Ng mentioned, I think in this context, is the idea that you should think of a task that the human can do in a very short amount of time. And this would be something that maybe a neural network can do pretty well, such as you show a human a photograph and ask them, is this a friend of yours or not? something like that. Or show a photograph and ask, does this photograph show a boat or not? So this a human can do, I think he gives some time, like under a second, half a second, so the human can do very quickly. And then this would be a good task for a neural network to do, and maybe is a good opportunity for automation. Other tasks that take a human a very long time, especially a very long time to think about and to plan, then maybe these are not the first tasks to think about. There are some online courses about deep learning, and it actually helps to look at as many as possible of them. So I will just list them here. Now there's new ones coming up every day, I won't say, but it's maybe every month. And so I'll just want to highlight this course, Stanford's CS231N, Convolutional Neural Networks for Visual Recognition. And so probably half the course is modeled after this introduction. There will be a lot of overlapping content, maybe even use some of their slides. So this is a very good course to get started with neural networks, to learn, let's say, the theory behind neural networks. It's not really theory, it's like a practical introduction to neural networks. And then there's another course, there's Coursera's machine learning course that is taught by Andrew Ng. This is if you feel and need more background in machine learning itself. This is also an easy course to take. And it's very basic, requires almost no prior knowledge, that can be taken by a wide audience, and that gives a very solid understanding of the basics of traditional machine learning. Now, for this course, also there is some background information, such as linear algebra or probability and statistic, where you have some online courses. It's probably a bit difficult to take a whole course in parallel to this course, just to get some preparation. And I guess it's not strictly necessary, but maybe you find it actually helpful to look at some selected topics, to review them using these online courses. But if you have the time, I definitely recommend to take as many online courses as possible. All right, so that concludes this section, and then I'll see you again in the next section.